Hello, good noon, sir.
Hello.
Hello, good noon, sir.
Yes.
Actually, sir, we has raised a query related to the assignment one, uh, question one, two, and three,
Okay.
but it is yet not solved.
Uh, Actually, I am not related with the assignment issue. So I'm only doing these problem solving sessions. I am not in contact with Professor Shabari or the other TAs who are handling the assignments and the solutions. So you can try to contact the NPTEL team directly or Professor Shabari directly if you just search for Professor Shabari's email ID. You can ask there what the issue is with the problem, because I saw the solution they had given. It was not uh, for 2% of ripple, it does not match. So
Hmm.
you can try to contact them directly.
Okay, sir. So we have to actually we had already put it that in the announcement, or sorry, in the student discussion, but yet nobody has replied to us. So that's why
Yes,
I
so
asked it.
they may not have opened that group to check the messages. So I think you should try to email them directly, whether the
Okay,
NPTEL
okay,
team or Professor Shabari directly.
okay, sir.
Okay.
Thank you.
Okay, so we can begin then for the second session of the problem solving session of the course, Design of Power Electronic Converters. The course is actually taught by Professor Shabari from IT Guwahati, but as I mentioned, uh, I'm a PMR scholar from IT Delhi, PhD scholar, and I'm just taking these problem solving sessions to summarize what was taught and just to give a sample of similar to the assignment and the problems you will get in the exam, but just to clear your doubts and uh, to show you how it is done. So we can begin with the summary of what was taught in the second week. Three topics will basically address. The first is the difference between the ideal switches and the non-ideal switches, which is the actual practical switches that you will be dealing with. And then two different devices, the diodes and MOSFETs, were taken up individually. Uh, we saw the characteristics and the datasheet terms that are provided and how to use them, how to understand them for the design aspect. So we can then start with the difference between ideal and non-ideal switches. So in the last week, whatever the converters we studied, we kind of assumed that the switches that we are using, they are ideal switches. So what does it mean to be an ideal switch? So basically, it means that if the switch is on, then it is just like a short circuit. There is no voltage drop, there is no resistance, and it can allow an infinite amount of current, and it can allow current in either direction, whether from the positive terminal to the negative terminal or in the reverse direction. So that is how an ideal switch would behave in the conduction mode. And when the ideal switch is off, then it would block any voltage, whatever we provide, whether in the positive direction or the negative direction, and whatever the magnitude of the voltage that is put across it. In the off state, the ideal switch will block uh, an infinite amount of voltage. And the third thing that is important for an ideal switch is that when it is transitioning from the off state to on state or vice versa, from on state to off state, it does so instantaneously. It does not take any time. And because of all these things, because there is uh, no voltage across it when it is on, and there is no current, leakage current when it is off, and because it is transitioning instantaneously, so then there will be no power loss in an ideal switch, because there will be no conduction loss, there will be no switching loss, and there will be no leakage currents and related loss. But of course, we know that there are no ideal switches in practical cases. In real life, we don't have any ideal switch. So we have certain limitations to the practical switches that are available to us. So first of all, they cannot block an infinite amount of voltage. If we increase the voltage blocking capability, then we have to then it will create some other problems. It will create a larger uh, resistance on resistance. It will create more switching losses. So, in practical situations, we are limited to how much voltage we can block. Similarly, when the uh, switch is off, then it will allow some leakage current, even though it is off. And similarly, when we turn on a practical switch or a non-ideal switch, there will be a slight voltage drop across it. There will be a slight resistance or a slight voltage drop, and that will create conduction losses. Similarly, there will be a limited amount of current that a practical switch can handle. It cannot handle an infinite amount of current, and it can most of the time the current that the device will allow, practical device will allow, will be in one direction only. For example, the diode can only allow current in one direction. Similarly, an IGBT can only allow current in one direction. A MOSFET can allow current in both direction, but that seems to be an exception rather than the rule. Similarly, voltage blocking is usually unipolar. Most devices cannot block uh, positive as well as negative voltages. And lastly, the non-ideal devices that we'll see, all of them take a finite amount of time to turn on and turn off. So when they're off, they're not carrying any current. When we turn that device on, it will take a time for the current to rise. And during the same time, the voltage will take some time to fall, and that will create some switching losses as well. So these are the problems that non-ideal devices are facing. And now we can look into some particular devices and to see their characteristics and how they are used and what information the datasheet can provide us. So first, let us look at the diodes. So three types of diodes were mentioned in the lectures. So these are the ones that are mostly used in power electronics. So first of all, if we have a rectifier application where uh, we have basically very high voltages and currents, but the devices are switching at a very slow speed. For example, if we have a 50 hertz signal, then the half cycle where the diode is conducting and where it is off 10 milliseconds, which is a significantly large time in uh, power electronic circuits. So that means these devices don't have to switch very fast. We can allow a slow switching device for rectifier applications. And the diodes that are used in these applications, they are called rectifier diodes or standard recovery diodes. So in these cases, we have very high voltage and current ratings. That means the conduction losses will be very small, relatively small compared to the other diodes, but the switching will be very slow. So that means because we are switching at very fundamental frequencies, 50 hertz, 60 hertz frequencies, the switching losses will not be that much at these frequencies. But if we use the same device, same rectifier diode at very high switching frequencies, then the switching losses can become too much. So that is why these rectifier diodes are used for rectifier applications where we have uh, high voltage and current ratings, but the switching requirement is slow. Next, if we talk about the DC-DC converters or SMPS applications, where we want to have very compact converters, so we require very high switching frequencies. In these cases, uh, the switching times of the diode should be very small. Otherwise it will take too much time to switch, and we will not be able to get. For example, here we have seen I'm showing a buck converter with 100 kilohertz frequency. So that means the total switching interval is 10 microseconds. But if the diode itself takes 1 or 2 microseconds to turn on or turn off, then that will take too much time. That will be too long. It will not allow us the normal operation at 100 kilohertz. So that is why we need very fast switching diodes in that case. And in that case, we use what is called Schottky diodes. So these are specially made diodes, and their reverse recovery, as we'll see, uh, isn't the reverse recovery does not take place. So these we can use for these applications. But The downside to these are they are available at very low voltages. So rectifier applications we can have in kilovolt range as well, and hundreds of amperes. So 2 or 5 kilovolt at 100, 200 amperes. But Schottky diodes are limited to 100 or 200 volts, and the current rating can be quite high, but the voltage rating is limited. And lastly, we have fast recovery diodes, and these are sort of intermediate between the rectifier diodes and the Schottky diodes. And these are used in applications where the switching speed is not too slow, but not too high as well. So 1 kilohertz to 10 or 20 kilohertz. And in that cases, we can use fast recovery diodes. So they do have a reverse recovery, but it is not as significant as rectifier diodes or standard recovery diodes. So these are the three types of diodes that were mentioned in the lectures. Now we can come to some the diode characteristics. So firstly, we can talk about the VI characteristics. So we can start with the conduction mode. So when we apply a forward voltage to the diode, uh, once it crosses what is called the threshold voltage, the diode will start to conduct. It will carry the current that is imposed upon it by the circuit. And those the how it will conduct and what is the voltage across it, what will be the voltage across it while it conducts, that is given in the VI characteristics. And if you see the VI characteristics here, it can be approximated as the current is zero until the threshold, and then it is almost a linear, it rises in a linear fashion. And that is why we can approximate this linear portion as an equivalent resistance. So that means as the current increases, linearly the voltage drop across this bit will also increase. So that will be the forward voltage across the diode at that time and at that current. And so this is the conduction area. And if we apply a negative voltage across the diode, then it will block that voltage and it will not allow any current except for what is called the leakage current. And the leakage current is usually very small. So here it is shown in an exaggerated manner, but usually it is uh, almost as small, very small so that it can be neglected. But if we increase the reverse voltage that we apply to the diode, a time will come at a certain voltage, then the diode will break down. So that is the breakdown voltage or the maximum blocking voltage that the diode can handle. And we are not supposed to go beyond this breakdown voltage. So this is about the diode VI characteristics. Then we can talk about the switching characteristics, how the diode turns on and how it turns off. During the turn on process, what happens is that the diode takes up the current that is in the circuit. So this is, we are talking about what is called clamp inductive load. So we have an inductor current that is first conducting by another device, and then that second device turns off so that the diode under that we are studying, it will turn on and it will take up that inductor current. And as the current rises, the voltage across the diode will keep on falling and it will reach zero. And then, but it would not stay at zero. It will actually go beyond zero to a positive current. And this is called the forward recovery. So why it happens is related to the diode, the physics of the diode and how there is some charge that has to be removed. And also it is related to the circuit parasitics. But in terms of the significance of this turn on process, it is the time it takes and the energy that is lost in this process is not very high. So that is why, uh, in terms of the switching characteristics of the diode, what we mostly talk about is the turn off process because the energy that is lost and the currents and the voltages that we get are more significant in the turn off process. So the turn off process, what happens is something called reverse recovery. So because the diode is a minority carrier device, when it turns off, the diode current first goes to zero while the voltage across the diode stays at around 0 volts. So this is just the forward voltage drop. And as the current goes to zero, it has to remove some of the minority charge from the diode. So that is why the current actually goes to negative first, and it reaches a peak which is called the recovery current IRR. And at that point, the voltage across the diode will start to become negative. And then it will take some time for the current to again go to zero. And this charge that is shown here in the gray shaded area, this is called the reverse recovery charge. And this charge has to be removed from the diode for the turn off process. And then there are different timings of this reverse recovery process. And the time T4 plus T5 is known as the reverse recovery time. And so this term is actually given in the data sheet. The reverse recovery charge is given in the data sheet. But all of these things are dependent on what was your the current at which the device is turned off, and how fast it turns off, the DIDT of this current, and the falling current. So these things will the charge and the time. These things will depend on the actual current and the DIDT of the current, and these things are provided in the data sheet. And we also have a term which is called a softness factor, which is given by the ratio of T5 time to T4. And depending on whether T5 is greater than T4 or T5 is less than T4, we can categorize diodes as soft recovery or abrupt recovery. Uh, and lastly, as I mentioned, the T on time is actually very small compared to the T off time. So that is why we will mostly in the data sheets, you will only find the T off duration and the losses that are related with the turn off of the diode. Now we can come to some of the datasheet parameters of the diode. So firstly, we'll see some voltage ratings, and these are basically the voltage that the diode can block. And many different kinds of ratings are provided in the datasheet. So for example, here I'm showing one device uh, that was actually provided as an example in the lectures. And as we can see, in the data sheet actually shows the maximum repetitive peak reverse voltage and the non-repetitive peak reverse voltage. So the repetitive voltage can be a voltage, a reverse voltage that comes across the diode repeatedly. So in every cycle, in every switching cycle or the fundamental frequency cycle, if this voltage, the voltage that is given in the data sheet, this is the voltage that the diode can block in a repetitive fashion. But that does not mean the diode cannot block more than this voltage for a short duration. And that rating is given by the non-repetitive peak reverse voltage. So this voltage is the voltage that the diode can block for a very short time if it happens uh, in a rare fashion. And as you can see in the data sheet, this voltage is slightly higher than the repetitive voltage because this does not come in a repetitive fashion. It does not occur frequently. That is why for a very short duration, the diode can block slightly higher than the repetitive peak voltage. Then we also have in the blocking state what is called the reverse leakage current. And the data sheet will provide values at certain temperatures, and the data sheet will provide typical values as well as maximum values, and it will also provide us some uh, waveforms or some plots which show how the uh, reverse leakage current changes with the reverse voltage. For example, here we can see that as the reverse voltage increases, the reverse current also increases. And as the temperature of the device increases, then the reverse current also increases. And this is a logarithmic scale in the current. So, as the temperature increases, the current increases by a very large amount. but still this current is quite much smaller compared to the forward current. Now we can come to the conducting state when the diode is in is forward biased and it starts to conduct. Then we are also provided with many current ratings. So it is similar to what was shown like the voltage. So the diode can handle some average current, but the peak current can go more than this average current. And if the peak current comes only very rarely for some transients, if the load changes suddenly, and in that case, the non-repetitive peak current can be much higher than the repetitive or the average currents, as is shown here in this datasheet example. So you can see that the non-repetitive peak current is actually 10 times the average current that the diode can handle. And these are mostly related to the temperature that the diode will go because of this current. So if you apply a large current for a very small duration, then the loss related and the temperature rise will not be very much. But if you keep on applying this current continuously, then you have to reduce the current to reduce the losses and the temperature rise. And next, we also have the forward voltage drop in the conduction mode. And this depends on the temperature as well as the actual current values. For example, here, if the current is low, then the voltage drop, the forward voltage drop will also be low. And as the current increases, the forward voltage drop also increases. So one thing you have to be careful is that this forward voltage drop is not the threshold voltage. It is actually the voltage, the threshold voltage plus the what we saw as the resistance of the diode. So for example, uh, for this device, the data sheet that is shown here, the threshold voltage may be around 0.15 volt or something. But as the current increases, the forward voltage drop increases. So at 50 amperes, the forward voltage drop is around 0.5 volt as is given in the values here. And as the current increases, the forward voltage drop also increases. And this is similar to the VI characteristics that we saw, but here the current is given in a logarithmic scale. That is why the shape of the curve is different compared to what we saw uh, as the VI characteristics of the conduction mode. Next, we can come to some switching characteristics, which are the reverse recovery characteristics. And as we see here, the data sheet provides the reverse recovery time, which is the negative current when it rises and then again falls. The total time is the reverse recovery time. And this is provided at different current values. So if the IF current is small, then the reverse recovery time will also be small. But as the current increases, so it goes from 1 ampere to 80 amperes, then the time it takes for the reverse recovery also increases. And the time also increases based on the temperature. So as the temperature increases, you can see the reverse recovery time increases by around 4 times. So that is why in these, when you are selecting a device, you have to keep into account what will be the temperature at the full load at the maximum uh, power handling uh, condition. And based on that temperature, you have to figure out what will be the reverse recovery time and what will be the associated losses. So here we also see the times TA and TB, which are the time that takes to the negative current to reach to the peak negative value, and then TB is the time from the peak negative to close to zero. And you can see here these two times are very similar. And so that is why the softness factor will be around 1 in this case. And finally, the reverse recovery charge is also given. And if you see in the curves for the data sheet, they will also provide the reverse recovery current. And this also depends on the DIDT of the current. As the DIDT increases, then the reverse recovery current So that this is the IRM peak, that also increases. And as the temperature increases, then the reverse recovery current also increases. And same thing is true for the reverse recovery charge. And this is understandable because if the current increases, the time duration increases with temperature, so the overall charge, which is the area under this portion, the negative portion, that will also increase. And all these details are provided in the data sheet. Next, we come to the thermal characteristics, and this is very important for diodes as well as the other devices like MOSFETs and IGBTs. And you actually need a slight background to understand this. So basically, what happens in the devices that we use, the device has a chip inside it, a silicon die, where the actual different layers, different the PN junction or the PNP layers of the MOSFET and the diode, they are present in this chip, and this is also called the junction. The temperature of this point will be called the junction temperature. And then around this chip, we have the casing of the device. And then this case we will usually put on a heat sink to dissipate the power that is lost, dissipate the heat that the device generates. That will be put on a heat sink to dissipate that heat. So the device will have different resistances between different points. So the first resistance will be between the junction and the case of the device. This is called the thermal resistance between the junction and case, and this will be provided in the data sheet. And then we will have another thermal resistance between the case and the heat sink, or this is the case to sink thermal resistance. And then we will have the thermal resistance between this heat sink and the ambient. And this will usually be provided in the heat sink data sheet and not in the device data sheet. And the ambient is the basically the temperature of the air that is surrounding the device or whatever. If the device is in some sort of liquid or some sort of gel or oil, then the ambient temperature would be the temperature around that device. And usually these different thermal resistances are provided in the data sheet. So if you know what power loss is happening in your device and you know these different thermal resistances, then you can find the temperature of each point. You can find the temperature of the heatsink, the case, and the thermal and the junction. And in the data sheet, you will be given a range of the junction temperature that the device can handle. And if the junction temperature goes beyond this range, then the device will be it will get damaged. So, for example, here we are one of the uh, data sheets. It provides the maximum junction temperature as 150 degrees centigrade, and it also provides the thermal resistance from junction to case. So that is the chip to the casing of the device, and then from the case to heatsink. And this is basically provided in terms of Kelvin per watt. And Kelvin per watt basically also means centigrade per watt. So basically, it means if you provide 1 watt of power from this resistance, this thermal resistance, then the temperature will rise by 1.4 degrees. And based on this, the data sheet will also provide the power loss, the total power loss, and as the current through the device increases, the total power loss will also increase. And so, for example, on the right side, you can see a figure is provided, and different curves are provided for different thermal resistances. SA, which is heat sink to ambient. So basically, if your heat sink has a very low thermal resistance, then the device can handle a higher amount of power loss. But if the thermal resistance of the heat sink increases, then the power loss that the device can handle, it also decreases. So the power loss is basically inversely proportional to the the thermal resistance of the heat sink. So a smaller thermal resistance of the heat sink will mean the heat sink is also bigger and it also has maybe some fan or some liquid cooling system. But basically, if you want to go to higher powers, then your heat sink thermal resistance should be as low as possible. So this was about the thermal characteristics of the diodes. Now we can come to the other device uh, that was taught in the lectures, which is a MOSFET. And it was mentioned in the lectures that the MOSFET is a bidirectional current device. So it can carry current in both directions from drain to source as well as from source to drain. It also has a inherent body diode inside the device. So that is basically, it is not uh, an additional device that is added to the chip, just like an IGBT, but it is inherently present in the MOSFET. You cannot remove this, uh, the body diode, and that also allows a negative current in addition to the negative current that is provided by the channel. But the MOSFET can only block positive voltages. So first, we can see the VI characteristics of the MOSFET. We can see what is called the output characteristics. So this is related to the drain source voltage and the drain current. So if the gate source voltage that which is provided is less than the threshold voltage, then we are in what is called the forward blocking mode. So that means if you the the MOSFET will not conduct any current. And once we increase the gate source voltage, then we will go into the active region, or sometimes called the saturation region. In this region, the device can carry some current, but at the cost of very high voltage across it, and this will create a lot of loss if we talk about power electronic circuits. So that is why we don't use MOSFETs in the active region or saturation region, but we prefer what is called the ohmic region. So that means the gate source voltage has to be high enough that we come to the ohmic region where the device basically uh, behaves like a resistor. So that means as the current across it increases, the voltage across it also increases in a somewhat a linear fashion. And based on the slope of this line, we can find the resistance, the on-state resistance, drain to source resistance of the MOSFET. So this is called the ohmic region or the linear region, and this is where we will operate the device when it is in the on condition. And in the off condition, it will be the forward blocking device. So in power electronics, we try to avoid the active region because our currents and voltages are very high. So in the active region, it will create a lot of losses that will uh, basically create the temperature of the device will be too much, so it will get damaged. Secondly, we also have what is called the transfer characteristics of the device, the MOSFET. And this is basically a plot between the gate source voltage and the drain current. And as the gate source voltage increases until it reaches a threshold voltage, the MOSFET will not conduct any current. And once it passes or crosses the threshold voltage, only then it will start conducting the current which is imposed upon it by the circuit. And this curve will also depend on the temperature, the drain source voltage. But in general, we can find the slope of this the in this waveform, and that will give us what is called the forward transconductance of the device. And these the curves and this value will be actually provided in some data sheets. Next, we have a very important concept, which is the switching characteristics of the MOSFET. And so this is basically how the MOSFET turns on and turns off based on the voltage that is applied across the MOSFET, across the gate source. So in and here again we are talking about what is called a clamped inductive load. So that means an inductor is we have a half bridge condition, and an inductor is connected to the midpoint and it is carrying some current. And then in the half bridge, one device is turned off and the other device is turned on, so that the current will basically shift from one device to the other. And how it happens is shown here. So we provide, uh, so first we talk about the turn on process. So when we provide a positive voltage to the gate, so first of all, the gate source voltage will rise slowly, and this the time basically it takes to rise for the gate source voltage to rise. It actually depends on the device characteristics, but overall it is very small in terms of the nanosecond range or microsecond range at maximum. And until the gate source voltage reaches the threshold voltage, there will be no change in the current as well as the voltage. Initially, the device is not carrying any drain current and it is blocking the full voltage that is applied across it. But once it crosses the threshold voltage, the gate source voltage crosses the threshold voltage, which is given in the data sheet, then the diode, the MOSFET will start conducting and the drain current will rise. And as the gate source voltage increases, the drain current will also increase. And once it reaches the full current that is of the circuit, of the inductor that is connected to the device, there will be slight overshoot based on the reverse recovery of the other device as well as some oscillations in the circuit due to some parasitics. There will be some overshoot, and then at that point, the voltage across the device will start to fall. And during this fall process, the gate source voltage will remain constant at what is called the Miller voltage. And then once the voltage, the drain source voltage is almost zero, then the gate source voltage will again rise to the full gate source voltage that we have given to the device, and the drain source voltage will fall to the on state voltage, which is the on state current times the RDS on of the device. So here we have different timings that will be given in the data sheet. We have uh, so first, based on when the gate source voltage starts rising to when it reaches the threshold voltage, so there is a delay. So in this time, there is no change in the current. So that is why it is called the delay time during the on process. It is given as TD on in the data sheet. And then the current starts to rise. So this is the rise time of the current. And then the voltage falls, which is the fall time of the voltage. And usually in the data sheet, TRI and TFV, these are not given separately. They are given together as the turn on time. So basically, when we provide a voltage across the gate source, as the voltage across the gate source rises to the threshold voltage, in that duration, the device does not conduct any current and the voltage across it remains the same, which is the voltage that it was blocking. And then once it reaches the threshold voltage, only then the device starts to conduct. And the drain carries some positive current from the drain to source. And then the drain current rises to the full value. And there is actually some overshoot because of the reverse recovery of some other diode in the circuit. And then once the full current is achieved, then the voltage will start to drop. And as the voltage drops, the gate source voltage remains at what is called the Miller voltage. It remains at that voltage, which is slightly constant. And then once the full voltage is the device voltage comes to near zero, only then the gate source voltage then again goes to the full value. And based on this process, we have different timings. First is a delay time from once the gate source voltage increases from zero and up till it reaches the threshold voltage. So that is the delay for the on process. And then we have the current rise time and the voltage fall time. And usually in the data sheet, this term is provided together. The TRI plus TF we will be provided as one time. And the reverse thing happens during the turn off process. So first the voltage, gate source voltage will fall slightly to the Miller voltage. And then during the Miller voltage, the voltage across the device, it will rise to the full blocking voltage. And thereafter, the current will drop. And the current will drop. As the current drops, the gate source voltage will reach the threshold voltage. And after that, the gate source voltage will go to zero. And similarly, we'll have a delay time during the off process and the voltage rise time and the current fall time. And you'll see which of these are provided in the data sheet. So next we come to some data sheet terms for the MOSFET. So here the voltage and current ratings are basically the drain source breakdown voltage. So for example, here we have the data sheet for this device that is written here. And here the drain source breakdown voltage is given as 200 volts. And there will also be given some conditions at which this breakdown voltage is given. So for example, you can see there is also a voltage temperature coefficient. So that means if the temperature of the device rises, then the breakdown voltage will also rise slightly. So for example, it is given at 0.24 volt per degree centigrade. So if it rises by 10 degrees centigrade, the temperature above 25 degrees, then the breakdown voltage will increase by around 2.4 volts. So that is also given in the data sheet. Next, we have the continuous and pulsed drain currents. So continuous current, for example, here it is given at two temperatures. One is at 25 degrees centigrade, which is 94 ampere. And then at 100 degrees centigrade, it is given at 66 ampere. So you can understand that as the temperature of the device it rises, then because if we allow very high current to go through the device, then there will be a lot of power loss and the temperature will increase further. So if the device temperature is low, then we have a larger temperature range that we can allow. So that is why the current at low temperature is higher than current at higher temperatures. And and here, this also is given at a VGS of 10 volts. And so if you see in the data sheet, you will be provided with these curves, which are basically the output characteristics of the MOSFET in logarithmic scale. And if you see as the gate source voltage increases, we go from the blocking region to through the active region to the linear region or the ohmic region. And the ohmic region is where we want to operate the device. And lastly, we will also be given the drain source resistance. So for example, here we are given the maximum value of the drain source resistance, and it is provided at a certain VGS and a certain uh, drain current. And this RDS is actually also dependent on the temperature. So here on the right side, this curve is also provided in the data sheet, and it is basically a normalized current. So that means at 25 degrees centigrade, the uh, the value of the drain source resistance is uh, 0.023 ohm. And then as the temperature will increase, the RDS will also increase. So for example, at 120 degrees, the RDS will become almost double. So it is twice the initial value, which is 0.023 ohms. So, so this is about the drain source on resistance. And in terms of gate related terms that are given in the data sheet, we have the maximum gate source voltage. So for example, here we are given as plus minus 30 volts. This is the maximum voltage that you can apply, and the There will not be, it will not damage the device. But this is not, it is not needed that we go to plus 30 or minus 30, because as we see in the forward characteristics or the outward characteristics, the at after 12 volt or 15 volt, these curves are almost similar. There is, but if we increase the gate source voltage beyond 15 volts, there will be no advantage to the, we will not get better, lower resistance, gate source resistance. So that is why we will only go up to maximum of 15 volt or even 12 volt is sufficient. So even though the maximum allowable rating for the gate source is 30 volts, 10 or 12 volts will be sufficient. And lastly, for the gate related terms, what will be given is the threshold voltage. So this is typically a range. It is not a single voltage. So for example, here it is given the minimum value of this voltage, the threshold voltage can be 3 volt, but it can also go around 5 volts. So between this 3 to 5 volt will be the threshold voltage. So the current will start to rise between this 3 to 5 volts. So next we have the switching related terms that will be given in the data sheet. So for example, we will have the gate charge. So these are different charges. So we have the total gate charge. So this is the total charge that is it takes from VGS equal to 0 to VGS equal to the maximum value, the 10 volts or 12 volts that will be provided. And then this is also, there are, it is split into different charges, the gate source charge and the gate drain mirror charge. And this you can actually see from the figure. So some portion of it will be the gate source charge. So the initial portion, which is as the gate source voltage rises, this will be the gate source charge. So around 45 nanocoulomb. And then the portion where the gate source voltage remains at the mirror voltage, this will be the Miller charge. And then the total gate charge will be the maximum value here at the 10 or 12 volt. And all these details are provided, and they are provided at specific currents and specific VDS voltages. And then we are also provided with the switching times, the turn on times and the turn off times. And the delay time is provided and the rise time is provided. And as I mentioned, the rise time is basically uh, uh, the rise time of the current plus the fall time of the voltage. And all these details are provided at certain conditions, whether what is the blocking voltage, what is the drain current, and it also depends highly on the gate resistance that we will probably will study in the gate driver week. Then we also have the parasitic capacitances of the device. And this basically, if we have a device with these three terminals, gate, drain, and source, there are some capacitances between the different terminals. And these three capacitances are basically shown here, but the datasheet will not provide us the value of these capacitances separately. The datasheet will provide us with the input capacitance, the output capacitance, and the reverse transfer capacitance, and how they relate to the capacitances between different terminals that is shown here. And even then, these capacitances are not what is called linear capacitances, or they are not constant values. They actually depend on what the drain source voltage is. And as you see in the figure, the capacitance is actually given in a logarithmic scale. So the change in these capacitances is actually quite large based on what the drain source voltage will be. So when we take care of these capacitances, we also have to consider what the drain source voltage will be across the device at that time. So this was all about the switching characteristics. Then we can come to the diode related or the body diode related terms, and this will be similar to the diode data sheet that we saw. There will be a continuous current rating, a pulsed current rating. There will be forward voltage drop, and there will be reverse recovery terms like the reverse recovery time, the reverse recovery charge, and they will be given under specific conditions. And finally, we'll have the thermal characteristics, just like the diode. We'll have the different thermal resistances between the junction to case and then case to heatsink. So this was all about uh, the datasheet terms. Now we can come to some problems that will be similar to what we saw in the what are given in the your course. So in your course, you are the assignment you are given a data sheet of a MOSFET, and you are asked to find different terms from that data sheet. So that is what we'll also do here. But before we do that, we can actually take a short break, a 5 minute break. So after that break, we will continue basically with this MOSFET data sheet, and we will basically find different ratings of the voltages, the currents, the drain source resistance, the times, and the charges. So we can actually take a short break. So we will continue at 4:05 p.m. Okay, so we'll take a short break. Okay, let us continue with the questions. So we are given a MOSFET and we are supposed to study the data sheet and find first of all the voltage rating. So if you see this MOSFET, if you search it and you can find the data sheet, the voltage ratings that are given is basically the drain source voltage maximum rating is 400 volts. So this is quite simple. There are no multiple voltages ratings, just one maximum voltage rating that is given for the drain source voltage, and it is 400 volts. Next, we are asked about the current rating. So here we have two terms. First is we are asked about the continuous current rating at 100 degrees centigrade, and then the pulse current rating. So if we see the data sheet, we will be provided with the continuous drain current at two different temperatures, and then we also provided the pulsed drain current. And if you see in the data sheet, we also provided a full uh, curve of how the drain current changes with the case temperature. And basically, as the temperature increases, the allowable continuous current rating of the device decreases. So the maximum temperature that this device can handle is 150 degrees. So if the case temperature is already 150 degrees, then the current rating goes to zero. So here we are asked about the continuous current rating at 100 degrees, which is directly given in the data sheet as 6.3 amperes. And we can also match it from this figure at 100 degrees, it will be around 6.3 amperes. And the pulse current rating is 40 amperes. So again, this is basically if you are providing some pulses of current. So instead of a continuous current, if the current has a pulse, so it turns on and then turns back off for some time. And depending on the duration of the current, which will be given in the data sheet, it is basically this rating is much higher than the continuous current rating. So here the answer is 40 amperes. Next, we are asked about the on-state resistance. And the question also gives us the test conditions. So we are given the VGS as well as the ID, which is the drain current. So if we see in the data sheet, for in the static parameters, we'll be given the drain source on-state resistance, and under these same conditions, and it is the value of this is basically 0.55 ohm. So this is almost 550 milliohm. And as I mentioned, this actually will change based on the temperature and the GS, VGS voltage and the drain current as well. But we are asked for a particular test condition which is given in the data sheet. So the answer will be 0.55. And next we are asked about the maximum gate to source threshold voltage. So again, if we see the data sheet static parameters, we are given 2 volt uh, voltages for the gate source threshold voltage. One is the minimum value and the other is the maximum value. And basically it is a range from 2 volts to 4 volts. And since the question is asking about the maximum value, so the answer to this portion of the question will be 4 volts. Next, we are asked about the total gate charge. So again, uh, this is provided in the data sheet. The gate charges, three different charges are provided. First, the total gate charge, and next we are provided the gate source charge and the gate drain charge. And this we can see from the figure as well. The gate source charge is basically the initial portion of the gate, the charge, and then we have the gate drain charge, which will be like the Miller portion of the charge. But since the question is asking about the total gate charge, so the answer to this will be the 36 nanocoulomb, which is the total gate charge. And actually, this will also depend on what the VDS voltage is. So, for example, here it is shown for three different voltages in the graph. And as the VDS voltage increases, uh, the total gate charge also increases. because basically as VDS increases, the Miller charge increases. So if you see, this portion of the graph changes depending on the voltages. So as the Miller charge increases, then the same is reflected in the total charge as well. So the total gate charge here is 36 nanocoulomb. So if the question does not give you the conditions, then you must assume that it is talking about the single condition that is given in the data sheet. So you don't need to refer to the graph. You can just find it from the tables that are given in the data sheet. So next we are asked about the typical turn on time of the MOSFET. And again, you can see the datasheet parameters, switching parameters. So the turn on time basically includes the turn on delay time and the rise time. So the sum of these two times, which is 35 nanosecond plus 10 nanosecond, this 45 nanosecond total is the typical turn on time. And again, this depends on the drain voltage, the current, and very importantly, the gate resistance, as we'll see in the gate drive lectures. This resistance is very important in determining how fast the device turns on and turns off. So this was about the typical turn on time. The next question is asking about the input capacitance of the MOSFET. And if we see from the data sheet, we will be given the input capacitance, the output capacitance, the uh, reference transfer capacitance, and then we're also given the output capacitance at different conditions. So the first condition is basically the VDS is 25 volts, and at 25 volts, uh, the output capacitance has different value, and as the VDS changes, the output capacitance value also changes. And this is, we can also see in the graph that as VDS increases, the output capacitance decreases. So at very low VDS, which is here at 1 volt, the output capacitance is 1490 picofarad, which is quite high. And then even if it increases by a small amount, so from 1 volt to 25 volt, then the capacitance decreases by a large amount because it is a logarithmic scale. But the question is asking us basically about the input capacitance. So we don't need to go to the graph. We will take the value given in the table because we are not, the question is not specifying any condition, any voltage, any gate source voltage or drain source voltage. So we'll just give the value that is given in the table. So it is 1030 picofarad. Next, we are asked about the maximum reverse recovery time of the body diode. So again, this is given in the body diode section of the data sheet. The data sheet will provide us the source to drain diode current. So it is a negative current from source to drain. And this should be, as mentioned in the lecture, it should be quite similar to the actual MOSFET current. And the diode also provides us the body diode voltage. So this basically is the forward voltage drop of the diode. But in this case, it will be the drop from source to drain, VSD, and it is given at specific voltage, specific current and temperature, and here it is 2 volts. But the question is asking about the reverse recovery time, which is TRR, and the maximum reverse recovery time. So here we are given a typical value and a maximum value. And the maximum value is 360 nanoseconds, which is the answer to this question. And as I mentioned in the summary, that the turn on time is actually very negligible. So that is why it is not given here. It is said that the intrinsic turn on time is negligible. So lastly, we have one question that is basically asking that uh, if we are designing a boost converter and we have to select the MOSFET and the diode, and the condition is such that the voltage rating of both of these should be above 75 volts and the current rating is about 10 amperes. And then we are giving some choices of MOSFETs and diodes. So we are supposed to search the data sheets of these MOSFETs and diodes and find which MOSFET and diode will be suitable, which combination will be suitable. So if you see the options, we are actually given two MOSFETs. So the MOSFETs in the option A and C are same, and the MOSFET in option B and D are same. So we are basically given two MOSFETs, and similarly we are given two diodes. The MOSFETs, the diodes in option A and D are same, and B and C are also same. So based on these, so out of these two MOSFETs, we have to select one MOSFET, and out of the two diodes, we have to select one diode. So let us look at the ratings of the MOSFETs separately. So, for example, one of these MOSFETs, the drain source voltage rating is 50 volts, and the continuous drain current rating is 15 amperes. Our requirement is 75 volts or greater than 75 volts and greater than 10 amperes. So the first MOSFET is basically the drain source voltage rating is not suitable because it is only 50 volts, but we require a voltage rating of more than 75 volts. So the first MOSFET is not suitable, and the second MOSFET has basically it satisfies our conditions because the drain source voltage is 200 volts, which is much higher than 75 volts, which we want. And similarly, the drain current, continuous drain current, even at high temperatures, is more than the requirement, 10 ampere requirement. So we can choose the second MOSFET out of these two. Next, we can also look at the data sheets of the two diodes, and we can see that both of these diodes have the voltage rating 300 volts. However, the current rating of the top one is less than what we require. It is only 6 amperes, whereas we require more than 10 amperes. So we have to choose the bottom diode, which has a rating of 30 amperes. So if we see which of the diodes and MOSFETs we had to select, the answer to this question is basically the option D. So because these two combinations of MOSFETs and diode will satisfy the requirements of the boost converter design. So the answer to this question would be D. So these are all the problems that we had. So if you have any questions regarding the problems or the theory that we discussed about diodes and MOSFETs, you can ask in the chat or you can unmute yourself and you can ask on the microphone.
Hello, sir.
Yes.
Hello. Sir, I have one doubt regarding IGBT and MOSFET. Uh, IGBT and MOSFET both can work as a bidirectional device, right, sir?
Uh, no, actually, the IGBT by itself cannot carry negative current. So in circuits where we have to use IGBT, we have to add additional diode to the IGBT.
Hmm.
So that is not the body diode like the MOSFET condition.
Okay.
So technically, IGBT is a unidirectional device. It can only carry current from the collector to emitter. But the MOSFET can carry currents in both directions.
Okay. Due-
Okay.
Okay. Due to the parasitic diode inside the MOSFET.
Yes, the
And sir,
diode, but
means IGBT is a unipolar, unidirectional device, and MOSFET is bidirectional device.
yes, the IGBT by itself is a unidirectional
And
device.
uh,
But if we can add a body
okay.
diode, so in
And
the
sir,
circuits that you
both.
see,
Okay, sir. And both devices are unipolar voltage devices, sir, because they are very poor in handling reverse voltage. So can we
Yes,
say that it is a unipolar devices,
yes, both of them are unipolar devices because the MOSFET itself has a body diode.
unipolar voltage
So
devices?
yes, the
Hmm.
MOSFET body diode
It
will
in
not
that case it is
allow any
clear.
reverse
Yes, sir.
flow. Okay.
Okay. But in case of IGBT, it is body diode is not there. So can it handle higher reverse voltages?
No, it still cannot handle reverse voltages. The IGBT, without the additional diode, it is still a unipolar device.
Okay. So both, sir, IGBT and both have different properties, right? One is bidirectional, one is unidirectional.
Yes, but that is not the only difference. There are also differences related
Okay.
to the internal mechanism, and that creates differences in terms of the ratings of the device, the switching characteristics, the losses. So there are other differences as well.
Okay. Actually, sir, one question in the assignment is there, and in that case, the options are offering same characteristics for the both the devices. So that's why I got confused.
Okay, so I will again suggest if you have any uh, questions related to the assignments, you try to contact the NPTEL team or the course instructors directly because, as I mentioned, I am not in contact with them. I just have to do this problem solving sessions to remove any doubts. So if you have any question regarding the first assignment or the second assignment, you try to ask them directly. You try to email them or you try to uh, you in the Swayam portal you can have some way to contact them directly.
Okay, okay, sir. Thank you.
Okay, any other questions? So if you have any questions, you can ask in the chat as well, or you can ask on the microphone. So I will be here for some time. So those who want to leave, they can leave. If anybody has any questions, I'll be here for 10-20 minutes. Yes, so the recording will be again uploaded on the same YouTube channel and the link will be provided. Uh, so in that Excel file that you have the link you have been given, you will be provided the recording and uh, the same folder, Google Drive folder, will provide the uh, presentation PDF. Okay, so thank you all for joining as well. Okay, there is a question of how to get the junction temperature from the data sheet. So the data sheet will not provide the junction temperature, but it will provide what is the maximum allowable junction temperature. So so uh, for example, if we see here for the diode, we are given the maximum junction temperature, which is 150 degrees. And the data sheet also gives the different thermal resistances. So for the junction to case and case to heat sink. And then you will have the thermal resistance of the heat sink to ambient. So that will be given in the data sheet of the heat sink. So once you have these three uh, thermal resistances and you know the ambient temperature. So for example, the ambient temperature can be 25 degrees if it is at room temperature, or if it is at an elevated temperature, then it can be more than that, maybe 30, 40 degrees. And then you know these three resistances. Finally, you also need to know what is the power loss that is happening in the device. So if you know the total power loss, that is the conduction loss plus the switching loss, so then basically you can create what is called a thermal circuit. So it is quite similar to an electrical circuit, but instead of current, you have the power loss or the heat in watts, and instead of resistance in ohms, you have the thermal resistance in terms of degrees per watt. And instead of voltages, you have the temperature. So based on that thermal circuit, you can find out if you know TA and you know the power that will be flowing through these three thermal resistances. In a sim, if you it's a simplified version of the thermal circuit, but you can then find out the heat sink temperature, the case temperature, and the junction temperature. So that it will depend on the power that is being dissipated, the current level, the switching loss, the switching frequency, all these things. So you have to make sure that whatever the temperature you get at the junction, it should be less than the maximum allowable case. So for example, here, your power loss should be such that the junction temperature does not exceed 150 degrees. So I hope that is clear. You're welcome. So if you have any more, if you want to understand this concept more, uh, you can try to search for MOSFET thermal characteristics. You will get some application notes which will give a better idea of how this thermal circuit looks like and how to give some examples of values, what is the power loss, and then what will you get as the junction temperature. So if you search uh, for MOSFET thermal characteristics, you will get some application note.
Hello, sir.
Yes.
Hello. Sir, if the we can we find out the junction temperature, maximum junction temperature from the
Sorry, can you repeat?
can we find out the maximum junction temperature from the RDS on RDS on versus temperature plot?
Uh, so that temperature is basically uh, the maximum temperature is given here, for example, in this table. So if you go beyond 150 degree, then you will damage the device. Then if within this limit, you can operate your device. So that is why you will be given different curves for what happens within this limit. So the RDS versus temperature, it will basically give you how the RDS changes as the temperature of the junction changes. And but it will not. That is not. It is not giving a limit. The limit is basically here. I mean, yes, the curve that is provided, the maximum point will be the limited point. So it will be given up to 150 degrees. It will not go beyond 150 degrees. But it is not like that. If the RDS is uh, a particular value, then you can find the temperature based on RDS. So the temperature is determined by the loss of the
Okay, sir.
device. Yeah, the loss will be dependent on the conduction loss and the switching loss. So based on that, you can find the temperature, and that temperature should be within 150 degrees or whatever is the maximum allowable temperature. And if it is between 150, let's say room temperature to 150, whatever the temperature is, you can find the RDS at that temperature. So basically, one thing you will
Okay,
have
sir.
to do
Thank you.
when you are doing the loss analysis. So first of all, you have to assume that, let's say, the device is at room temperature. Then you find out the loss. So at that point, you will get the one value of RDS from the datasheet. But once you find out the loss, then based on the thermal circuit, your temperature will increase. Then your RDS will also increase, and your loss will also increase. So if you want to find an accurate uh, loss or temperature, you have to do it in an iterative fashion. So you have to first assume a temperature which is like the ambient temperature. Then you have to take the RDS value at the ambient temperature. Then you have to find the power loss. Then you have to find the junction temperature. Then based on that junction temperature, you have to update the value of RDS, and then again find the loss, again find the temperature rise. So it will be an iterative process, and after some iterations, you will converge to a value. The temperature rise and the power loss will converge to some value. So, I mean, that's a bit complicated, but if you want a more accurate picture, that is how you can do it from the data sheet.
Thank you, sir.
Okay, so there is one more question about why I forward is 1 ampere if uh, okay, so let me go to the diode portion. Okay, so I think it was for the diode data sheet. So just a minute. So is it this one you were asking about? So basically, the reverse recovery time is given for two conditions. So like this is the how the waveform is looking like. So you have the device is carrying some forward current and then it is turned off. So then it will have some DIGT, the current will fall, and then it will go to the IRM, and then it will go to zero, and it will take some time TRR. So now the TRR actually depends on what the forward current was. So if the forward current is only 1 ampere, then the typical value of TRR is 46 nanoseconds. But if the forward current was different, so if let's say you have in your circuit, the circuit is now carrying a higher current, so that the forward current of the diode is 80 amperes, then the TRR will also increase. It will increase from 46 to 74 nanoseconds. So basically, what this is basically saying is that the TRR is dependent on the forward current that the diode was carrying when at the moment that it was turned off. So I hope that is clear. So because this is the test condition, and so it also depends on the IF. It will also depend on DIGT. So some data sheets will give the TRR at different DIGTs as well. So even though here it is at the same DIGT, uh, but some data sheets can give it at different DIGTs as well, and then the TRR will again change. So Naveen is asking about delay time in MOSFETs. So actually that will be given in the data sheet how the times are defined. So if you look at the end of any data sheet, they will have a figure like this, and they will then define which one is the delay time and which one is the rise time and the fall time. But usually the delay time is this one when the gate source voltage goes from zero to threshold, and then you have the on time or the rise time. Uh, so, for example, yes, you have the turn on delay time, you have the rise time. So this rise time is basically in this case TRI plus TFV, and it will be given for let's say 10% of current to some uh, 90% of current or something like that. And so they define it in the data sheet itself what they mean by the rise time and fall time. But in general, the rise time will be TRI plus TFV, which is the rise time of the current and the fall time of the voltage. And similarly, uh, the fall time is actually the turn off process. So usually it will be TRV plus TFI, but you can check in the data sheet as well. Exactly. So in one of the last pages, They will provide, let's say, the test circuit and the definitions of the turn on time, turn off time. So reverse transfer capacitance um, basically is the CGD. The reverse transfer capacitance, which is written as RSS, CRSS, is basically the gate to drain capacitance. And this is actually very useful because once you know the CRSS, you can uh, you can basically isolate CDS and CGS from the CISS and COSS because you just have to substitute for CGD. So the definition of CRSS is given here, and then based on CRSS, you can figure out what is CGS, and CDS. Uh, why VDS must be greater? Greater than what? Can you clarify your question? Okay, VDS greater than 75 volt. So basically, uh, it means that the circuit that we are operating, for example, here it was a boost converter. So the boost converter circuit, uh, the output voltage of the boost converter will be such that the voltage that will be applied on the switch will come out to be less than 75 volts, somewhere around 75 volt. So if we use a MOSFET whose rating is less than 75 volt, then the MOSFET can break down. Let's say you have a boost converter and the output voltage is 75 volts. Then if you use a MOSFET with a rating of only 50 volts, then as you try to go to 75 volt output, your MOSFET will break down. So you will not be able to reach your uh, 75 volt output. So uh, you cannot use the boost converter as intended. So that is why you have to use a device whose rating is above the rating, above the output voltage that you require. So that is for simple understanding. But actually, if you want an output voltage of 75 volt, you cannot just take a 75 volt MOSFET because you have to provide some safety factor because there are oscillations and overshoots. So you need to get at least like 1.5 times the the voltage rating. So basically here it is saying that the voltage rating should be above 75 volt. So we can probably assume that the output voltage is around 50 volts. So that is why a voltage rating of above 75 volt should be safe. But basically the purpose is that if we have a low voltage device, then it can break down. We will not be able to operate the boost converter at the full voltage. So I hope that is clear. Uh, No, why would the MOSFET be less than 75? Because as we saw in the last class, in a boost converter, the voltage that has to be blocked by the MOSFET is basically the output voltage. So if the output voltage is 75 volt, the MOSFET should be able to block at least 75 volts. Okay, so basically you have to again go back to the circuits and you have to find out the on equivalent circuit, the off equivalent circuit, and then see what is the voltage that is imposed on the device. And based on that, you can find out what will be the required device voltage rating.